Write down the exact state of a patch of space, hand it your differential equation, and walk away and expect the future to be determined. That is how physics normally works. But imagine the same system and suppose the equations hand back something that you did not put in. Extra choices, extra degrees of freedom. Strange, yes, and dangerous for theory. Even more so for people who bet on these predictions. Roger Penrose asked the question directly, is there a cosmic censor that keeps nature from showing us naked singularities? If the answer is no, then predictability that we take for granted in general relativity fails. But if the answer is yes, then maybe the worst thing that can happen is that our equations quietly break down and quarantine behind horizons. And we can use this theory as usual. Those two options surprisingly define how seriously we must take the theory of gravity, something that claims to be deterministic. The entire scene was caused by two revelations. The first, singularity theorem, showed that collapse generically makes singularities, places where curvature blows up and the equations stop making sense. Their second discovery was that anything inside the event horizon, including the singularity, would be sealed off from the rest of the universe. Weak cosmic censorship says, when singularities form and collapse, they're hidden behind event horizons such that distant observers never see them. In other words, the universe covers its mess for the outside observers. The strong cosmic censorship is a different beast. It asks, given the data on an initial slice of spacetime, is the future determined up to the point where the theory itself truly fails? If the answer is no, then there exist spacetimes where you need extra information later to keep predicting. That is not just a hidden singularity. That is, a failure of determinism inside classical gravity, meaning the theory gives multiple possible futures and trajectories if you're close enough to the black hole. Now, mathematicians immediately began to make counter-arguments. Christodoulou pretty much showed that naked singularities can actually form, depending on its initial conditions. Then, he made a significant add-on. Those initial conditions are extremely sensitive. He's basically saying it's possible to balance a pencil on its tip, but also useless to consider it practically. So, in a way, naked singularities do exist, but you just have to nitpick and fine-tune the setup to get them. That tends to favor the censorship idea in practice, but it's also certainly not a decisive argument. Another line of research came up with a physical shield. Poisson and Israel, followed by Ori, discovered that the inner horizon of a charged or rotating black hole can experience something called mass inflation. We talked about mass inflation in this video if you want more depth, but essentially, any perturbations like light waves or gravitational waves that approach the inner horizon gets an increase in energy without bound. For light, they get more blue shifted, and tidal forces become infinitely large, causing discontinuity between the predictable universe and the unpredictable inner horizon of a black hole, called a Cauchy horizon. This is a very clear mechanism that is tending to support the censorship wall, at least in many classical scenarios. So far, so good. Counterexamples exist, but many are fragile. Mass inflation seems like a reliable wrecking ball for a lot of would-be extensions, but the plot thickens. The twist? Around 2018, a number of teams asked, what if black holes were in a universe with a positive cosmological constant, meaning a universe that expands in an accelerating rate, so faster and faster over time? In fact, that is quite literally our universe. This choice affects how perturbations die away outside the black hole. In these kinds of spacetimes, certain groups of people discovered an effect that seems to be very significant. The incoming perturbations decay so rapidly that there might not even be enough incoming energy to strongly induce mass inflation. Simply saying, the outside can be so quiet as to not cause the inside to explode. For example, linear analyses of near-extremal charged black holes with de Sitter expansion may indicate that the inner horizon stays normal and the metric can be smoothly extended, not discontinuous. That would be a counterexample to the strong cosmic censorship in that specific scenario. People first reported those results and, of course, surprised many researchers and opened up technical debate. The discussion is very intense and sharp, however it's also completely truthful. Some follow-up works argue the non-linear effects or additional matter fields causing the blowup, while others emphasize the exact sense of extendable. Could it be that we're inquiring if the metric can be continued in a continuous manner, or continuous with first derivatives, or with square integratable curvature? alter that technical requirement and the decision could be reversed. So the takeaway is that the result depends heavily on the assumptions and definitions used. There are three main ways researchers attack the problem. Each is useful, but none is a single silver bullet. For example, mathematicians can demonstrate under specific assumptions that extension is impossible by using comprehensive partial differential equation theorems. However, definitive outcomes are often limited to symmetric or simplified settings, but they're the sorts of results I can trust. Second, physicists approximate the decay rate outside the inner horizon. The blue shift can cause a curvature singularity if the decay is slow. The blue shift may not happen if the decay is fast. Though it is only indicative, it serves as a set of diagnostic criteria. And third, compute numerical relativity, basically brute force. Here, people saw full equations on a computer and watched the insight evolve. This is very complicated and also costly, but it is a reality check. When numerics agree with mode estimations and theorem, confidence grows, and when they disagree, you dig deeper. These combined factors are not a simple yes or no reply, but rather a map. In most astrophysical situations, the classical arguments of mass inflations appear to be quite persuasive. Linear analysis leaves a space which numerics and partial differential equations, people can either close or confirm, particularly in the vicinity of a near extremal and de Sitter parameter ranges. But what if the censorship fails? Honestly, for everyday astrophysics, probably not much. Most black holes we detect are not extremely charged black holes in de Sitter space, but conceptually it is big. If the classical theory can produce regions where predictability fails, then our philosophical and technical basis for predicting how gravitational systems evolve over time is weaker. Can any of this be tested by observations? Just a bit. Gravitational wave measurements allow us to determine those decay rates very accurately. Thus, we limit whether the exterior is quiet enough to allow an extendable interior. The process is indirect but feasible. Enhanced detectors will improve the test considerably. If you want to watch something that might move the needle, look to three areas. First, math. Sharper PDEs, partial differential equations, results that precisely identify which versions of the strong cosmic censorship remain valid under physically reasonable assumptions. It certainly takes a lot of work, but the results are very decisive. 2. Computation. Nonlinear evolutions with longer times and more realistic matter content are being used in computation. Those runs, however, are still very costly, but they serve to confirm how reliable the linear picture recommendations are. Third, observation. Improved gravitational wave spectroscopy and improvements in horizon-scale imaging. Even if we were never able to see the singularity, we could still study the decay channels and late-time behavior that govern the interior. Nobody, certainly not me, would be satisfied with a simple yes or no answer. And I think having a detailed map that shows where the classical determinism holds and where it breaks is better. This gives engineers and observers guidance on the locations where they need to focus on their work, and tell physicists where they need to bring in quantum gravity. In the end, cosmic censorship is not an easy to solve puzzle. We may never know whether the universe has a cosmic censor, but that appeals to me. Maybe it appeals to you too. If you made it this far into the video, you're probably that kind of person who enjoys sitting with uncomfortable questions. So, if you want more of that, you know where to find us. Hey guys, sorry for sounding weird if I do in this video. As I'm recording, I'm sick right now, so yeah, thank you for watching.